So this next video is going to cover part 1 of thermodynamics and equilibrium. This is from chapter 18 of your book. First, some review. The first law of thermodynamics. Basically, the idea here is that we have the law of the conservation of energy, which is basically the first law of thermodynamics. And it's summed up that in a closed system, energy cannot be created or destroyed. Energy can be transferred from one system to another, but the total energy remains constant. So if you think back to the idea of a calorimeter has insulated walls, and so the insulated walls you can take as the assumption that energy cannot enter or leave the calorimeter, but it can be transferred. So like if you have water and a hot metal piece inside the calorimeter, the heat can be transferred from the hot metal to the water, but it cannot be lost or it cannot be gained in terms of the total energy inside the calorimeter. This leads us to talk about Hess's law and the idea that the total energy released or gained from a chemical process is equal to delta H. Delta H is what we call the enthalpy. This is the enthalpy. And basically, enthalpy is usually expressed as kilojoules or joules per mole. Okay, and it is the sum of the moles times the heat of formation of all the products, and then you subtract it from the sum of all the moles of the heat of formation of the reactants. Okay, and we did this in 151, where we found the delta H for various chemical reactions by taking the sum of the heat of formations of the products, subtracting the sum of the heat of formation of the reactants. And so the calculation will tell you whether or not this process that you're looking at is endothermic or exothermic, and you can really divide it into two kind of categories. If your delta H is negative, i.e. it is less than 0, we say it is exothermic. And remember that the idea exothermic heat is released, okay, and is a product. So if you're thinking back to Le Chatelier when we talked about it, if it's exothermic, that means if you have A gives you B, heat is a product on the right-hand side of the arrow. If you have delta H and it is positive, a positive value like plus 500 or plus 30, whatever that is, plus, then we say that it is greater than 0 and it is endothermic. Oops. Endothermic. Okay. And again, that means that heat is absorbed for this reaction to go forward. And if you remember from Le Chatelier's principle, if you have A going to B, when you have endothermic, heat is a reactant or on the left side. All right. This is just a review of what we've already learned in 151 and also what we learned in terms of the Le Chatelier's principle. So if you have a spontaneous, before we go on to that, the idea of endo versus exothermic basically tells you that heat is either released or absorbed as a result of a chemical process. It doesn't actually tell us if a reaction is spontaneous or not spontaneous, okay? This idea of spontaneity means, does this reaction occur if it's just sitting there, okay? It's just sitting there. Will it occur? Will it not occur? That's the idea of spontaneity. Now, once it occurs, whether it releases or absorbs energy or heat, that is addressed with the idea of enthalpy and exo and endothermic. But that is after the fact that it has occurred, okay? So really this idea and this kind of new idea that we're going to be looking at is really has nothing to do with whether or not heat is absorbed or released. It has to do with whether the process is spontaneous or not. And we have a new term here. This new term is called entropy. Not enthalpy, but entropy. and it is represented with the variable S. All right, so the change in entropy would be delta S, for example. Okay, and so we can identify a spontaneous process as a physical or chemical change that occurs by itself. It requires no continuing outside force to make it happen. So if you have, say, for example, a ball sitting at the top of the hill and you let go, the fact that the ball will go down the hill is a spontaneous process. You don't need to do anything to it. It will just, you don't need to apply any force. It will just start rolling down the hill. Okay? In this particular case, we would say that entropy is positive. So here, entropy is a thermodynamic quantity, and it is a measure of how dispersed, okay, the energy of a system is among the different possible ways that the system can contain energy. Okay? And the book defines it as saying the more disordered the molecules are, the higher the value of entropy. Okay? The more disordered or dispersed, okay, the energy is in a system, then we say the higher or more positive delta S is. So if we look at it in terms of pictures, because a picture often is worth many, many words, okay? If you're comparing ordered versus disordered, what is ordered, what is disordered? If you see here in the picture on the left, this is highly ordered. Everything is arranged in a very orderly lattice. All the pieces fit together, okay? This is more disordered, okay? This is an increase in entropy, right? So here the entropy value will be higher because it is more disordered, okay? Another way to look at it, if you have ice is basically water molecules in a very ordered fashion. That's six-fold symmetry. So this is order. Disorder would be if you melted it and it became water. So all the water molecules are all jumbled together. Okay, again here, you're what we call increasing the entropy, or delta S is greater than 0. Okay, this is just a pictorial representation of what we just talked about in words in the slide before. So this leads us to talk about the second law of thermodynamics, wherein it says the total entropy, and again I repeat, entropy is represented by the variable S of a system and its surroundings always increases for a spontaneous process, okay? So this is the kind of three-part you need to remember. Entropy increases, it's a spontaneous process, all right? Or as I like to think of it, everything spontaneous tends towards a more chaotic or more disordered system of energy. The total amount of energy remains the same, but it is more dispersed. So a mathematical expression of the second law is basically delta S, or the change in entropy, is greater than Q over T. However, if a reaction is at equilibrium, then delta S is equal to Q over T. Okay? And so the book says delta S, the entropy of the system, is equal to delta S of the universe is equal to delta S of the system plus the surroundings. And in our universe, that entropy or that amount of energy is always greater than 0. In other words, things are getting more and more chaotic. So, again, the second law of thermodynamics, this is again a pictorial representation. You have here N2O4. So I've represented N2O4 as one molecule, and so it's a big clump, okay? And what happens, it becomes 2NO2. So this one molecule is becoming two distinct separate molecules, right? So you've got here one molecule of N2O4. Here you have two molecules, one of NO2 and one of NO2. Okay? So you would say that if you had something that's one molecule becoming two things, it is getting more disordered. Okay? And those two parts are more disordered because they can move in all kinds of different directions and in all kinds of different speeds versus the one molecule by itself. Okay? So in the reaction in breaking one molecule into two smaller ones creates more disorder, in the sense that the two NO2 molecules can now move independently. In this change, the molecular disorder increases. This is important, okay? As does the entropy, okay? So if you are breaking down something and it's the result of, oops, I'm going to write that neatly. If the result of the reaction is more molecules, or more particles, if you would like to think of it, that means that you have more disorder, and that means your delta S has increased, okay? Because your entropy has increased. All right. So, of course, we always like to do a little bit of math, and this is just an example. You have the heat of vaporization, delta H, of carbon tetrachloride, CCl4, and that heat of vaporization is 39.4 kilojoules per mole. So if you have 1 mole, basically what this reaction is, it's saying something liquid is becoming something gaseous, okay? And that change of state is a delta H of 39.4 kilojoules. So if 1 mole of liquid carbon tetrachloride has an entropy of 216 joules per Kelvin, what is the entropy of 1 mole of the vapor in equilibrium with the liquid at this temperature, okay? So really, you know that when it's in equilibrium, delta S is equal to delta H over T, okay? So really, delta H is equal to 39.4 kilojoules per mole, and T is 25 degrees Celsius. Of course, we're going to change it to Kelvin by adding 273, okay? So really, we need to solve for delta S here, okay? To solve, we're just going to stick in our delta H and our T, and we get delta S, or the entropy value for this process of vaporization, is 132 joules per Kelvin. So basically what it's saying is, if you have liquid, the entropy value is 216, okay? When you have something in equilibrium, so you have some gas, some liquid, okay? The disordered amount is this amount. This is the amount of disorder. The amount of disorder that is introduced or added by vaporization. Okay. And that makes sense, right? If you have something liquid and it's becoming a gaseous state, the gas is even more disordered than the liquid. It can take up more space and more volume, so it is more disordered. And so because it is more disordered, the delta S value should get larger. So the criterion for a spontaneous reaction, right? Ultimately, we would like to know what would be some of the things that we can identify that we can use to say, oh, this reaction most likely will be spontaneous. Ultimately, the question is whether a reaction will be spontaneous, because if it is spontaneous, it will occur without any outside force. So we have this equation here, delta H enthalpy is subtract the temperature in Kelvin times your delta S, which is your entropy, okay, is less than 0. Then it's spontaneous at constant temperature and pressure, okay? So if you predict that it is less than 0, you predict it is spontaneous. If you predict that this value is greater than 0, then it is not spontaneous. And if it is equal to 0, it's at equilibrium, okay? So then we get to the third law of thermodynamics, and it states that a substance that is perfectly crystalline at 0 degrees Kelvin has an entropy of 0. Now remember, when something is at 0 degrees Kelvin, it has no translational, rotational, vibrational energy. It has none of that going on. It's all the molecules are perfectly still, okay? And so when that is at the case, the system is 0 degrees Kelvin and it has no entropy and there's no disorder because the molecules are basically at a standstill, not moving, okay? Now delta S values, like all state functions, are experimentally determined and will change if pressure and temperature is changed. So for example, if you have a phase change, so if you're going from solid to liquid or liquid to gas, every time you do a phase change, you should have an increase or a decrease in delta S. If you're going from solid to liquid and then liquid to gas, every one of those phase changes should give you an increase in delta S. In fact, a large increase, because if you're going from solid to liquid, you're introducing quite a bit of disorder, because as a solid, everything was in its ordered state, and as a liquid, everything is jumbled up. Now, when you're going from a liquid to a gas, not only is everything jumbled up, but now it can have the freedom to fill whatever size container you have, and all the molecules are moving at much higher speeds. So there is more disorder. So we say phase changes it results in large increases in delta S, okay? And for the entropy at 1 atm and 25 degrees, it's what we call the absolute entropy, and we signify this with the degree symbol here, okay? So really, this degree symbol here tells us that it's at 1 atm and 25 degrees Celsius. So in this particular case, entropy will increase if any of these three rules apply. A reaction in which a molecule is broken into two or more smaller molecules. We saw this already. So for example, if you have one molecule and it results in lots of little molecules, okay? Delta S would be positive, okay? A reaction in which there is an increase in the moles of gas, okay? And this may result from a molecule breaking up, in which case Rule 1 is also related to Rule 2. And a process in which a solid changes to a liquid or a liquid or a gas, or a liquid changes to a gas. So basically, if a solid becomes a liquid, a solid becomes a gas, or a liquid becomes a gas. All of these things, we're getting more disordered, so therefore, delta S would be greater than 0. And so, here there's a nice little chart. You can see that they have delta S or disorder on the y-axis. And every time you go from a solid to a liquid, you have this big change in delta S. And a liquid to a gas, there's another big change in delta S. All right. So we would like to predict, based upon our three rules, the sign of the entropy. So let's look at 3 examples. Okay. A, you have glucose. It's a solid. Okay. And it becomes ethanol, liquid, and carbon dioxide, gas. Okay. So based on our rules, is it negative or positive? Is entropy negative or positive? Okay. In this particular case, delta S is positive. Let's look at rule 1. You have a large molecule becoming 2 smaller molecules. You have glucose, and it's becoming ethanol and carbon dioxide. Okay? So in this particular case, rule 1 says they should be positive. Rule 2. Rule 2 says that if you have an increase in the moles of gas, and that is indeed the case. You have 0 gas here. You have 2 moles of gas here. Okay? So again, rule 2 would predict also positive. Rule 3, you have a state change from a solid to a liquid and gas. Solid to a liquid and gas. Again, that fulfills rule number 3. So in all 3 cases, Rule 1 and Rule 2 and Rule 3 predicts delta S is positive. Okay, let's look at another example. NH3 plus CO2, it becomes urea and water, liquid. Okay, so let's look at rule number 1. You have 3 things, it's becoming 2 things. So you have 2 moles of gas, okay? 2 plus, let's just call it 3. You have 3 particles, okay? And then here you have 2 particles. Okay, so that is the opposite of rule number 1, okay? Then rule number 2, you have 3 moles of gas and no moles of gas, 0 moles of gas, okay? And you have a gas becoming, right here, a gas becoming liquid, okay? So that's the opposite of rule number 3. So therefore, in all 3 cases, it does predict that delta S would be negative, okay? Because it is the opposite of rule 1, 2, and 3. Last but not least, if you have carbon dioxide gas, water gas, and it's becoming carbon monoxide gas, becoming carbon dioxide gas and H2 gas, okay? Rule number 1, it's saying you have 2 and 2 particles, so all the same. Rule number 2, you have 2 moles of gas and 2 moles of gas, so all the same. Rule number 3, you have a gas becoming gas. So in this particular case, this is wrong. In this particular case, everything is at equilibrium, so delta S is equal to 0. Because all 3 rules, none of them apply. All right, we're looking at the 3rd law of thermodynamics, and we're going to learn how to calculate delta S. Delta S is basically the sum of the moles of the formation of S products minus reactants. So let's look. And this table is in your book, and this table is also in the back of your homework booklet. Okay. Now, I really would take this particular chart that's in your homework booklet and find it. It should have a entropy. And you can identify it because it has S on it. So I would get a pencil and write really, really big on the top of that delta S, and then put it in a box like this. Because one of the most common mistakes is you're going to get the S table, the entropy table, mixed up with your enthalpy table, and then it's going to get all mixed up, and then you're going to be pulling entropy values when you want enthalpy values, and et cetera, et cetera. So if I were you, I would pull this table out from your booklet and put at the top of this where you have S, delta S, so you don't get confused. It's just my take on things. I would really do this. All right, so what you're going to do is you're going to find calcium solid. Its value is 41.59. So I would bring down the 2 as well, because this is the number of moles. So 2 times 41.59, okay? Oxygen gas is, let's see here, it's kind of blocked, 205.0. You guys see that here? 205.0. And 1 is the stoichiometric coefficient, so we're not going to bring that down. It would be pointless. For the calcium oxide solid, it is 38.21. Okay. So here you've got your reactants. And here you've got your product. Okay. Now if you're looking at this formula, it is the products subtract the reactants. And it's the sum of the reactants, so you need to add your calcium values and your oxygen values, the sum. Okay, so if you do this math really quickly, 2 times 38.21 minus 2 times the sum, of 2 times 41.59 plus 205. I'm getting, you should check my math, I'm getting minus, 211.76. My units should be in, notice here, the units should be here, or joules over K mole. Okay? Or mole K. I like to write K mole. All right. So basically, this is how we did Hess's law with delta H values, except now we're pulling delta S values from this table. All right. Let's look at another example just to make sure we know how to do this. Okay, so we're looking for NH3, that's right here, 192.7. So we're going to say 2 times 192.7. Okay, carbon dioxide is the first one. So again, there is a stoichiometric value of 1, so we're not going to bring that down. That would be pointless. For the NH2CONH2, it's not on this abbreviated table, so I looked it up for you. It is 174. And for water liquid, it is 70 joules per kmol. So really, again, we're looking, and these are the reactants. These are the products. Okay, so really for delta S, we're going to say products, and that's the sum of the products minus the reactants, and it's the sum of the reactants. You should probably write just a little bit smaller. Okay, so if you're doing this all the way through, let's see here, 174 plus 70 minus 2 times, okay, so this comes out to approximately, I'm going to round it a little bit, minus 356 joules per kmol. All right, so we're going to stop here. I would suggest that you watch this video and do the homework up to this point, and then watch the next video and do some more homework problems. I will post a second video